Hello, my name is Latrice Hall. I'm a second year PhD student at Florida International University, and our research looked at a novel use of a machine learning algorithm for studying spatial language development. So, we talk about how objects, people, and spaces exist in the world by using spatial language. And this refers to words that describe features, shapes, locations and directions, dimensions, orientations, and others as well. The use of spatial language by parents and children appear to be relevant components in this complex system of factors that predict entry and success in science, technology, engineering, and math. So, in recent years, researchers have increasingly looked at the development of spatial language. But to our knowledge, there has only ever been one naturalistic longitudinal language sample that's been coded and analyzed for spatial language. And this was done by researchers at the University of Chicago. But we fully understand that naturalistic longitudinal studies are optimal for truly capturing development or change over time and in an ecologically valid way. So we can't help but to think that a major reason why there's a lack of this type of research is perhaps because spatial language is inherently context dependent and it requires a great deal of time and effort to code. So let's just take the word left, for example. If I were to say, please give me that pen to your left, this would be a spatial usage of the word because it communicates the relative location of the pen. It's to your left. However, if I were to say, I think he left town yesterday, this would not be considered a spatial usage. And there are dozens and dozens of potentially spatial words that can be used in hundreds of non spatial contexts. So you can start to see how examining the context of each potential spatial word before classifying it as indeed spatial is a daunting task. And this process has traditionally been done manually, whereby a researcher will look at the context of each potential spatial word, but to ensure that it is spatial before considering it for analysis. So, in an attempt to address this, we've turned to the naive Bayes classifier. It's a supervised machine learning approach that's used in classification tasks, such as filtering spam from email and sentiment analysis, which is pretty much a process that analyzes text to determine whether the writer's attitude is positive, negative, or neutral about that written subject. Well, we investigated whether this algorithm could essentially do the same type of thing with spatial language, such that it accurately classifies utterances as spatial or non spatial. So, to use a supervised machine learning techniques such as naive Bayes, one would take a portion of their data set to train the algorithm and then use the remaining unseen portion to evaluate the performance of the model. To do this, we gathered transcripts from the homeschool study of language and literacy development, which was available on the Child's TalkBank system. And this was a naturalistic longitudinal study of 83 American English speaking, racially diverse preschool age children. We specifically looked at the toy play sessions in which parents and children engaged with blocks and puzzles and pretend play because these are the sessions more likely to contain spatial language. So, first, we dichotomously coded roughly 500 utterances as spatial or non spatial, according to the spatial language coding manual developed by Kedden and colleagues in 2007. And we'll call this collection of coded utterances Dataset A. Then we used R to train the naive Bayes algorithm with dataset A. Then we coded another set of new utterances, which we'll call dataset B, and used this to evaluate the model. After the model was evaluated, dataset B was added to dataset A, and then we trained a new model with both A and B, and we'll call that model AB. So then we coded a new set of utterances, which we'll call C, and evaluated model AB with dataset C. And this process was repeated. After we evaluated a model with unseen data, it then became a part of the new training data set. And then a new set of utterances were coded and used as the new test data set. And so we did this until the model performed at or greater than 0.70 when evaluating unseen data for 3 consecutive iterations. And the evaluation metrics that we used were accuracy, sensitivity, and specificity. And we'll talk more about those in just a bit. But after a total of 3,913 utterances were coded and tested, with approximately 40% of those being spatial, we reached our 0.70 threshold. And then we moved into the phase where we evaluated 4 test transcripts without adding anything else to the training data. So pictured here are the results from our final 4 test data sets, which ranged from 266 utterances to 938 utterances for a total of 2,229 evaluated utterances. And it's important to reiterate that these utterances were from 4 completely different studies that had not been used at all for training the model. The children in the studies were between 2 and 6 years of age, and the parents and children engaged in a variety of activities, such as free play with toys, blocks, puzzles. They talked about book illustrations, and some even completed Piaget conservation tasks. So, as I had mentioned, we evaluated the model performance with 3 metrics that are commonly used with classifiers. So the accuracy metric is the percentage of correct predictions for the test data. Now, this model correctly predicted between 85% to 92% of the utterances, which is really, really good. The sensitivity metric is essentially the true positive rate, or it identifies the proportion of spatial utterances that were correctly predicted as being spatial. The sensitivity of the model ranged from 0.72 to 0.88, which is pretty good, but there is definitely room there for improvement and consistency because this is really the crux of our study. We want to detect and classify spatial language. And then finally, the specificity metric is indicative of the true negative rate or the proportion of non spatial utterances that are correctly predicted as being non spatial. And the specificity of the model ranged from 0.87 to 0.94, which is almost perfect classification. Now, these findings are really encouraging because they suggest that the naive Bayes classifier can indeed code spatial language, and it can do it in a fraction of the time that it takes using traditional methods. So, we're currently working to improve and optimize the model for more fine grained spatial language analyses. And we hope to disseminate the methodology, the R syntax, and the training data set to encourage investigators to conduct naturalistic longitudinal studies that can further elucidate children's spatial language development. So I really enjoyed talking about this subject, talking about our project. So please feel free to email me if you'd like to talk further or if you have any questions, or if your lab has de identified transcripts that you'd be willing to share. Thank you so much.